Okay, welcome everyone to the second part of the workshop. Yeah. So yesterday we saw the basics of neural networks and what deep learning is, and we saw how it's useful as function approximators. And we also compared it with the other existing methods, particularly projection methods that you might have seen in grad school. Today we'll see some deep learning principles. We'll spend some time on optimization techniques, because that's really at the heart of deep learning. So we'll spend some time on what gradient descent is and some of the variants of gradient descent. And we'll think carefully about activation functions, pros and cons of each of those functions, and why parameter initialization is important. We saw weights and biases are the parameters of the neural network, and it's important to initialize them properly, especially in a deep neural network architecture. And we'll see some examples of how things can go wrong when you don't carefully initialize the parameters. And I'll also talk about some object-oriented programming principles, very basic classes and objects. We will not get into inheritance and polymorphism, but to understand how macro model interacts with the machine learning part, it's important to understand some basic concepts of object-oriented programming. And then in the later part of the course, if possible today, we will also look at some applications of a macrofinance model. But before going into the code, we'll first think carefully about what kinds of PDEs that we normally encounter in macrofinance and how we can approach them using the tools that we learned in the first two parts. All right, same references as yesterday for the first two parts, and for the third part, I will provide references later in the third file here. Cool. So yesterday we saw how learning by trial and error worked in helping the loss function go towards 0. And I also told you that more principled way of doing this guesswork is what learning is all about. So when you see deep learning, deep is all about the architecture of the neural network, especially when you have lots of hidden layers, then it becomes a deep neural network. And when you have more principled way of finding the parameters of the neural network, that's what learning refers to. So let's see how, what is this principled way of doing this guesswork, and how should we think about this? So let me go back to this graph yesterday that we saw. We had a simple problem to approximate 2 data points using sigmoid activation function, just a nonlinear function here. We had a very simple architecture, one layer, one neuron per layer, sigmoid activation function, and that's it. We wanted to approximate these 2 points. And because there are only 2 parameters in this neural network, we can plot the loss surface. And let me go back to the first data point. We started with a random guess here, and that mapped to the loss surface here. And as we moved in that direction, loss actually increased. But as we took improved random guesses, we were going towards the right direction, and eventually loss became 0. So just by inspecting this loss surface, it should give you some idea about how to design a principled way of reducing the loss. Okay? If you are here, it just basically means that you go towards the valley in the direction of the slope of this loss function. Okay? That's basically what gradient descent is all about. So we have parameters weights and bias in this simpler problem. So I have the same problem in mind. You have 2 data points, 1 neuron, 1 layer. So there are only 2 parameters, weights and bias. And you start with a random guess for W and B, and the goal is now to update W and B. How do we do it? We start at some random point, and that gets mapped to the loss surface, and we compute the gradient, which is the derivative of the loss with respect to weight at the iteration t. T refers to iteration here, and we use that to update WT. Okay? There are 2 parameters, so for each of the parameters, this is the gradient rule. You start with some initial value, and then you update this by looking at the loss with respect to each of the parameters. And this eta here refers to the learning rate. The idea is that you want to go in the direction of where the slope is, but you don't want to go all the way down. So this parameter eta is typically 0.1 or 0.5. It's typically less than 1. Okay? You don't want to go all the way down in the direction of slope. You just want to go a little bit in that direction. Okay? And that also, this is also a hyperparameter that you can tune. Okay? Now, in this simple example, there are only 2 parameters. And so the learning rate is said to be the same for both. But there is no reason for why this learning rate should be the same. Learning rate can be different as well. For example, think of a situation where you have a high dimensional problem, and there are some sparse features along one particular dependent variable, okay? or independent variable, let's say in a regression problem. When you have very sparse data points, and when you train the neural network, the learning algorithm will not see a lot of points in that dimension. And therefore, those particular parameters will not be updated often. Okay? But those sparse data points may be important for you because that sparse dimension may capture some important economic feature of the problem. Okay? So in order to force better learning corresponding to that sparse dimension, you could also adjust this learning rate. So this is one example where you would want to have different learning rates for different parameters. Okay? I'll make all of this concrete when we go to add a grad. All right, so what is this gradient here? That's simply the derivative of the loss with respect to the parameter. Okay? There are 2 parameters, that's why it's a partial derivative. Now, T here refers to the iteration. Again, eta is the learning rate. Learning rate is a very important parameter. That's the first thing that you typically hypertune when you play around with the learning model. Okay? Now, you typically compute the gradient at the iteration T, but later we will also see different ways of computing those gradients. All right, sometimes the update equation is written simply like this, but this is a coding convention. Just don't be confused when you see an equation like this. This should be read as left arrow here. So W gets updated by this amount. And this is typically how you write in Python. So people also use the same notation in slides. So, all right. Now here's the algorithm. First, this is the first iteration. Initialize it, maximum iteration, because you don't want to keep running forever. So just set it to 1,000. And as long as the iteration is less than the maximum iteration, you just keep upgrading the weights and bias. Okay? And then you increment the iteration. So that's the algorithm. Let's go back to understanding how to actually compute these gradients. Yeah? I showed you it's the partial derivative of the loss with respect to W. I'm going to show you some simple algebraic equations, but I want you to carefully think about the implications for the computer. Okay? So whenever you see these simple algebraic equations, automatically think about if you were to write this in the computer in Python, how memory gets allocated, what is the implication for that, implication of that in the learning process, and how you can efficiently improve that. Okay, so here's the problem. You have a mean squared loss. The first thing that you want in a learning process is to define a loss function. This is a simple problem, so it's just a mean squared loss. Y is the output, and F is the approximation. ANN stands for artificial neural network, which, this is the architecture, single layer, single neuron. I didn't denote W and B here, but it's kind of understood. Weight comes here, and bias comes here. Weight gets multiplied by X, added to bias, and fed into activation. Remember, aggregation and then activation, and then aggregation and activation in a deep neural network, but this is a simple artificial neural network. So you just aggregate and you activate. All right, cool. So how do we differentiate? You just do some, little steps of algebra here, which I did not include in the slides. But basically, when you compute the partial derivative with respect to the weight, this is what you get. And this is if you have just one data point. Okay? Now, what happens if you have 2 data points? You basically do the same for each of the data points, and you aggregate them. Okay? Now, this sounds simple, but what happens when there are millions of data points? Okay? This goes from I equals 1 to 1 million, okay? Which means that you're computing the gradient by aggregating all these 1 million data points before you update the weight even once. Okay? This has profound implications for learning, and this also relates to a question from yesterday, why we need stochastic gradient descent and what's so stochastic about it. Okay? All right, so you have two parameters. So update them using the same rule, except that if there are million data points, you want to sum across those million observations. How do we do it in Python? You have two data points here. And the first thing you want to define is the activation function. I'm showing you in Python notation here, but eventually, a few slides down the line, we will go to TensorFlow, but the steps are the same. So that's why I introduce you to the very basic Pythonic environment so that it's easier for you to map later to TensorFlow. First thing you define is activation function. So here, the activation function is sigmoid, and NP refers to NumPy. If you're new to Python, just import NumPy. And NumPy is a class that has an object, math object called exp, which computes the exponent. Okay, cool. The next thing that you need in the machine learning algorithm is the error. That is the loss function, right? So here, the loss function takes two parameters as inputs, w and b. You set the error to 0, and then for each data points, you compute the sigmoid function, and then you compute the error. This is important because for each x, y in this whole data point sequence here, capital X, capital Y, which refers to these two vectors, you have to aggregate the loss, okay? And then you return the error. The next is to compute the partial derivatives. Okay? Here, we know it in closed form, so I can just write simple functions. But when you go to TensorFlow, you use automatic differentiation. But the skeleton is the same. First, you define what activation function to use. Then you define your loss function. And then you compute derivatives using automatic differentiation. And then what you do, you train the network by gradient descent. This is plain vanilla gradient descent. The algorithm is what I showed you earlier. You have some initial data points, -2 and -2 for weight and bias. And you have a learning rate. Typically, it's less than 1, but this is a simple problem, so I'm just going to set it to 1. Okay? And I have some maximum number of iterations. And then for each points in your vector, you compute the gradients. And once you have the summation of all the gradients, you update the weights and bias. Okay? In the folder, I have a file called gradient descent. If you want to get your feet wet, what you can do is you can copy this part, okay, and just execute this and try to plot the error for each iteration and see what happens. So I just want you to have an intuitive feeling of how loss gets reduced as iteration progresses. This is important because later we'll also compare this with some momentum-based gradient descents to see and compare the differences. Okay? Now first, just take 2 minutes, try to understand this code, and then try to plot the loss as a function of the iteration. Okay? If you have a nasty PDE problem and you're trying to use gradient descent, it's just going to take forever because probably there are lots of plateaus in this loss function. Okay? So let's look at a way to improve this, and that's called momentum gradient descent. So basically, the idea is that navigating plateaus take a long time since gradients are very small. And the whole idea is that if you're being repeatedly asked to move in the same direction, then it's a good idea to walk faster that direction. Okay? How do we do that? In the gradient descent, you were updating with respect to the loss, with respect to the partial derivative of loss with respect to the parameters. But now we are going to look at the past updates. Okay? So if the past updates all point in the same direction, then you work faster. Okay? The way to see this is to rewrite this algebraic quantity like this. And here you can see that UT is basically the exponential weighted average of current and past gradients. Why is it exponential weighted? Because you want to attach more weight to the very recent observations and less weight to the distant past observations. Okay. Now, how do we code this? You have the same thing, similar to stochastic gradient descent. WB are initialized. You have a learning rate of 1. And the only change is that instead of upgrading the weights and bias by the partial derivatives, you look at the history, okay, before updating. For Zoom participants, what I'm sharing is I'm sharing my Jupyter notebook in Colab. I hope you can all see. What I was showing earlier is that I was plotting the loss of gradient descent as a function of iterations, and the upgrade was much slower here because you were stuck in a plateau. Okay? And if you're being asked to repeatedly move in the same direction, it's a good idea to walk faster, and that's what momentum gradient descent does, and that's what I show here. Okay? Here you see that the updates here are much larger, and you achieve, you're moving towards the global minimum in a much faster fashion. Yeah. All right. All right. So that's what Nesterov accelerated descent does. It fixes the problem that once you fall down the cliff, you're going way past the global minimum. Okay. What it's doing is that it's adding a look ahead property into the gradient descent. You have the same equation here. Here in the plain vanilla gradient descent, you had eta times the gradient, whereas now you're going to replace that with a look ahead property. What does it mean? Instead of updating the gradient at iteration t, you update the gradient at iteration t plus 1. Okay? Right? So in a gradient descent, why is this important? Because look ahead basically tells you that when you're going down the hill and when you're about to reach global minimum, and when you compute the gradient at the valley, then the gradients are going to be smaller, which means it's better for you to apply brakes. Okay? So this look ahead property allows you to apply brakes when you're really going down the hill towards the global minimum. That's the idea. Okay? All right. So these are all the basic variants of gradient descent. There is nothing stochastic about any of this. Right? At each iteration, you update the weights by looking at all the observations. Okay? Why is that problematic? Because when you have millions of observations, then what you're doing is that for every update that you do for the parameters, you're looking at millions of observations, and that may be suboptimal. So a better way to do that is to compute these gradients for each observation. You see one observation, you update the gradient. You see the next observation, you update the gradient, so on and so forth. Okay? So for the moment you see 1 million observations, you've already made 1 million updates. Okay? But the problem is that it's a very noisy estimate of the gradient. The best estimate of this gradient is to see 1 million observations and then compute the gradient. Okay? That's the best you can do. But that's slower. So stochastic gradient descent is basically computing the gradient for each observation. Okay? That's why it's stochastic. What that also means is that when you plot the loss as a function of the iteration that I like the ones that I showed you earlier, it's not going to be smooth. Loss is not going to monotonically decrease. It's just going to have some zigzag and wavy fashion. It'll just oscillate around because each gradient estimate is a very noisy estimate. And therefore, what it's doing is that it's updating so each gradient is favoring the data point that is in front of it, ignoring all the other data points that it's not seeing. Okay? Yeah. So it's stochastic because, first of all, it's a noisy estimate of the true gradient, right? The true gradient is the gradient that you compute after observing all the observations. But when you compute the loss just after seeing one observation, it's very stochastic. It's very noisy estimate, and it will make the loss very stochastic as well. That's the idea. In the models that we have in mind, what are the observations? These observations will be the state variable and the value function itself. Yeah, they're simulated. They're simulated. This is for, I'm just showing you for a broader set of problem. For example, you can think of this as a simpler regression problem, or X can be variables from the state space and Y can be a value function, right? It's the same problem. but it's much broader. Yeah, you sample uniformly. I will get to it, but the rough idea is that you sample uniformly from the state space, and that's your X. Okay. So when you code it, what happens is that instead of in a gradient descent, for each update that you do, you compute the gradients by after seeing all the observations. See here, for each XY, you compute the gradient and you keep accumulating, and then you update. So for each, you're just making very few updates if you want to wait for 1 million observations. The improvement in stochastic gradient descent is that it's a very simple change. All you're doing is you're just pushing these updates in the inner loop here. When you push those updates in the inner loop, then you're updating these parameters very frequently. For each observation that you see, you compute the gradient and you update the parameters. Okay. All right, this makes the descent stochastic, and that's precisely because the parameters are updated in the direction that is most favorable to it without being concerned about other points. And this is why there is no guarantee that at each step, the loss function is reduced. It's not going to monotonically reduce. It may oscillate. And sometimes the oscillations can be very wild. Okay. So how can we prevent that? We can use mini batch gradient descent. What mini batch gradient descent does is instead of updating after seeing each observation, you want to update after seeing random 100 observations. That's all there is to it. And batch size refers to how many data points that you want to see before you make an update. That's what batch size is. And that batch size is also a hyperparameter that you want to play around and tune. Different models have different optimal batch sizes. And you typically have a grid where batch size is anywhere between 1, which is stochastic gradient descent, and n, which is the total number of data points. In that case, it's just gradient descent. And on a log scale, you just pick random values and you repeatedly solve the model and see which one gives you the best loss. By best loss, I mean the loss that's closest to 0. All of this is refers to training loss. Remember that the problems that we have in mind, there's no issue of overfitting necessarily, because we have a functional approximation problem, right? And so just pick the one with the best training loss. And if you want, you can split it into test set and data training set, and then pick the one with the best test loss. But it's not going to matter much for the problems that we have in mind because it's a functional approximation problem, and we want to have the best training loss. Yeah. Oh, yeah. That's a good point. In fact, one of the advantages of using stochastic gradient descent is that, or mini batch gradient descent is that, because at each time you're computing gradients by looking at different set of observations, it's less likely that you'll be trapped in a local minima. Okay? When you make these gradient updates, the way you navigate through the loss surface is that when you receive different samples of data at each iteration, the way you update will be such that you're not bound to be towards local minimum. And then that's just results from experimentation. I'm not sure if there are theoretical results that tell you that stochastic gradient descent can help you avoid local minimum for sure. But this experimentation tells you that when you have mini batches, then it's less likely that you'll be trapped in a local minimum. Yeah. Oh, there is a question.
Yeah, can I ask you quickly? So maybe I'm missing something completely. But if you go to the comparison between the stochastic descent and just the regular descent, like this previous slide, yeah. So here, in the gradient descent, suppose I have 2 points, then my dw is going to be the sum of 2, right? dw1, dw2.
Yes.
And then I'm going to subtract that times eta from my w. And in the stochastic gradient descent, I will first subtract dw1, and then when I go to the next point, I will then subtract dw2. So I don't really see why, in the end, my w and b are going to be different for these two codes.
So that's a good question. What we are doing here is that once you see the first data point, you just immediately compute W and B, right? You're updating. And for the next data point, this will also affect the loss function.
Oh, I see. Get it. Okay, thanks.
Yeah. All right. Cool. I think the easiest way to see is to plug this quantity here. Here you see that when you have multiple data points, this function is a function of vectors, right? This x is a vector, so that's how it gets affected. Okay, where were we? There are many more variants of this gradient descent. First is note if you notice the previous formulas, we were always using this eta, which is the same. And we were not really adjusting this eta. This eta is the learning rate. And I told you that it's an important parameter in the learning process. It so happens that in some cases where there are sparse dimensions, and if in particular, if those dimensions are important features of economic model, then they should be updated more often. And that's what ADA-grad does. A similar variant is root mean square and ADAM optimizer, which is an adaptive momentum optimizer. And they all just varies the learning rate in some form or the other. What I show here is an update rule for ADAM. Again, let's start from the last equation, which is very familiar to us. In plain vanilla gradient descent, this is just eta. And this will be the gradient. Okay? What we are doing here is that we are also accounting for the history through this M. This M gets updated like this. Why is there an adjustment term? This is just a bias correction term. If you look at this equation, the expectation of this M quantity is the same as the expectation of this gradient, right? And so this M basically captures the history of gradients. This is why it's a momentum optimizer. But not only that, the sparse features need to have a higher learning rate because this learning rate basically accelerates the update. And that's what this V does. This V captures the second moment of this. The expectation of V is the expectation of this, which means that it's the second moment. And you basically adjust the learning rate based on the second moment. Okay? This is a very popular optimizer. In fact, this is considered to be the most widely used optimizer today in machine learning. And one of the reasons is because it has these two nice properties that it not only accounts for the momentum, but it also adjusts for the learning rate. Yeah. All right, cool. So the bottom line is there are lots of variants for stochastic gradient descent. Everything boils down to how you adjust the gradients and how you adjust the learning rate. And these two parameters are very important when you hypertune. All right, cool. So let's go back to how to compute those loss function. There's a typo here. Sorry, there should be a bracket. So I told you that we typically upgrade the gradients by computing the partial derivative. And when you have a simple architecture like this, it's just trivial. But when you have multiple inputs, then you compute the gradients by computing each of, or you update each of the parameters by computing each of the gradients. Okay? Now, what happens when you have deeper architecture? What happens when you have deep layers? Typically, you have loss function like this. Okay? And that's why when you have complex problems, we have deeper layers. And when you have deeper layers, there's something called backpropagation. Backpropagation is basically the application of chain rule. If you want to compute partial derivative with respect to W1, which is here, then what you do is you start from here and you basically repeatedly apply chain rule. Okay? Again, all of this is very trivial algebraically, but I want to force you to think about memory implications, and especially the property of aggregation, activation, this sequence. Okay? Sorry about the typo. This should not be here. So you compute derivative of output with respect to activation A3, and then derivative of A3 with respect to activation H2, so on and so forth. But let's take this one. Okay? What is H2? Remember, A is aggregation, H is nonlinear activation, right? And I told you this is important because the activation has to be nonlinear. Otherwise, it reduces to a linear problem. Now, why is this important here? This is not important because aggregation is affine, but here you have a nonlinear function. Okay? And when you have complex basis functions, computing this is very costly. When you have a really deep neural network with 10, 15 hidden layers, then you're computing these derivatives repeatedly. And especially when you have different basis functions in each of the layers, then it becomes just computationally costly. So it's much better to have simpler basis functions so that computational overhead is much lower when you compute the gradients. All right, so why is having a deeper architecture relevant? Because we repeatedly compute these derivatives, and when you have complex basis functions, it's problematic. So it's important to use simpler basis functions. Okay. Now, this is also a simpler deep neural network. Why? Because there's just one neuron in each hidden layer. Okay? This is one hidden layer, this is one hidden layer, but there is just one neuron here. What happens when you have multiple neurons? You do the same backpropagation trick. Okay? You compute the loss, except that now you have to pass through multiple neurons. If you want to get to x2 from here, then boom, boom, boom. Okay? And that's why having a wider architecture would also mean a larger computational head, because when you backpropagate and compute these gradients, you have to pass through all of these guys in the hidden layer. Okay? And a little bit of terminology, backpropagation actually means you want to compute, you want to update the loss by computing the derivative with respect to the input. So you're backpropagating from the output to input. And forward propagation means you pass an input and you just compute the output in each of the layers. Okay? That's just terminology. Okay, there are different kinds of activation function. I told you that's sigmoid is a simple one. A problem with sigmoid function is what happens when the input is very large in absolute value. Sigmoid is just throws you 0 here, right? Not only that, the derivative of sigma with respect to input is also 0. Why is that problematic? Let's look at backpropagation here. This H2 is the activation function, right? Which means this is basically sigma of some input. What happens when that input is large? This derivative is 0. Okay? When you have a deep architecture, somewhere when the derivative is 0, this gradient becomes 0. Okay? What happens when this gradient becomes 0? W is not updated anymore. Okay? This is called as a vanishing gradient problem. That when the input to a sigmoid activation function is very large, then the derivative or even the function itself is going to throw you 0 values. And that means that the learning breaks down. Okay? Sigmoid is simpler, but it also is problematic. So it's a good idea to make sure that the inputs are all clustered around 0. Then what happens when all of them are tightly clustered around 0? Then the activation function is almost linear. Then it kind of boils down to a linear regression problem. So you want to make sure that it's spread around 0 such that there is enough dispersion. That's the point. Yes, that's right. One can do that. And in fact, I think 2 slides down the line, I'll show you how to properly initialize the parameters such that at every layer, you have inputs that is clustered around 0, but with enough dispersion such that you don't have vanishing gradient problem. Okay. There's a systematic way to do this. Okay, another question? Yeah, so if you stretch it too much, then it almost becomes linear in most parts of the state space, right? You also want to have the nice non-linearity property, but at the same time avoid vanishing gradient problem. Okay. It's true that's a good way to do it, but another systematic way is to make sure that you're taking advantage of nonlinearity, but at the same time. Okay. For PDE problems, tan H is very popular. It behaves just like sigmoid, except that the output is between -1 and 1, but it's relatively computationally expensive to compute. For computer vision problems, the ReLU activation function is the most widely used, precisely because it's super simple, like computationally very cheap. The gradients are like 0 and 1. Here, again, the problem is that when inputs are very large in magnitude, your gradients are 0, which will, again, cause vanishing gradient problem. So you have the same, you need to make some parameter initialization such that the inputs at each hidden layer are around 0 with enough dispersion, such that you take advantage of nonlinearity and avoid vanishing gradient problem. Yeah. Yeah, you could do that. So there are like lots of alternatives. Yeah. So well, this here you have one exponent, right? And it's kind of repeatedly used here. So you're just basically doing it once. Yes, exactly. Compared to ReLU, it's expensive, right? Other than that, it's roughly similar. So to avoid the problem that when inputs are negative, the output is 0, there's something called ReLU, but now there are like 10 other activation functions, something called CELU, something called XELU, swish activation function, so on and so forth. We won't get into all of them. Tan H is our friend, so let's just move on. But if you find a better activation function that works for our problem, I'm happy to learn. All right, let's think about weight initialization. Assuming tan H is the best friend that we have, we want to make sure that the data points are spread around here. So let me show you a simple example where things can go wrong. Okay. I have an example with 10 hidden layers, 500 neurons in each layer, and tan H activation function. And the parameters weights and bias. Let's forget about bias. Let's just focus on weights. The weights are distributed randomly, random normal distribution. Input dimension and output dimension corresponds to the number of input and output dimensions. But so this W is actually a vector, okay? And this one corresponds to the number of hidden layer. The first hidden layer, you initialize weight like this. And all we are interested in doing is we're just doing forward propagation. So there's no learning or anything here. All we are doing is that we have some random inputs, we have weight distribution, you aggregate it, you pass it into tan H activation function, you take the output, you multiply with weights again, and then you pass it, so on and so forth. Okay? So what happens when we do that? The first layer, we have weights normally distributed, okay? And so the aggregation is also normally distributed. And as we move forward, as we keep forward propagating, all of the output is getting centered around 0. Okay? And this is basically the vanishing gradient problem. The reason this happens is because when you have 500 neurons in each layer, you're aggregating across all these neurons, and the input becomes so large. The input into the activation function in the next layer becomes so large. When input is so large, your sigma, the derivative gives you 0. All right. So in the final layer, you would end up just having 0 values, and that means that the learning shuts down. So this loss becomes 0, and therefore W does not get updated anymore. All right. How do we fix this? A simple trick to fix this is called Xavier initialization. What these co-authors did is that they realized that when you have lots of neurons in each hidden layer, it makes sense to scale it. Because when you add 10,000 small quantities, it ends up becoming large quantities. So let's just scale it by 10,000 again. Okay. This simple trick restores learning. And the way we see is we plot the mean of the output from each hidden layer here. And we also plot the distribution. And we see that compared to the previous case, points are scattered around 0, okay? Which is good for us because when you backpropagate, learning will not be shut down. Okay? These gradients will not be 0. Here it's just this only this part is different. So when you have 500 inputs, the total output becomes large. So you just scale it by 5, square root of 500. Okay? And there's something called her initialization, which is basically square root of input dimension plus output dimension. And there are other ways to do it. There's something called glorot. But I just want you to be aware of all these issues because when you code in TensorFlow, you have to provide what kind of initialization you want. And if you just provide uniform, you're dead. The learning is going to be shut down and it's problematic. So you want to make sure that there are enough points around 0 with enough dispersion such that you take advantage of nonlinearity at the same time restore learning. Yeah. It's similar except that in batch normalization, I think it's similar. Yeah. So the question is if it is similar to batch normalization, which means batch normalization is basically you take the output from each hidden layer and then you normalize it, like you would do in a regression problem, right? In a regression problem, you just normalize the regresses before you feed into the learning process. Here you're doing that for every hidden layer, not just at the start, but for every hidden layer, you do batch normalization. It's similar. Perhaps there are some advantages and disadvantages between these two approaches. I can't remember, but it's roughly in the same spirit. Okay. Okay, so that's all I have for the basics of deep learning. Let's get into some programming. I want you to get familiarized with some basic object-oriented programming stuff. Now, it's a whole full semester course in itself. There are lots of things like inheritance, polymorphism, encapsulation, and abstraction, so on and so forth. We will not get into all of these. We will focus on what classes are, what objects are. And the reason we'll focus on these two is because the closest thing to library that I have is a class. And basically, this class is a way for you to update the value function. So you can write another class, which is your macro model. And that allows you to interact with the class that I have to update the value function, which is basically a deep neural network algorithm. Okay? And that's why learning classes are important. What is a class? Well, it's just basically a collection of objects. If you've used struct in MATLAB, it's basically the same thing, okay? Except that it's slightly more flexible. And the Python syntax is closer to C++. So in that sense, the transition will be slightly bigger for you, but the concepts are same. If you've used struct, class is similar to struct. Okay, so how does it look like in Python? I'm going to use Pythonic notation, but as you will realize, it's very closer to C or C++, sorry, not C, C++ and Java if you have used before. So this is how you denote. You have a class called model. So you call it model, and you have the two functions. And the first is a default function, which is called init, which means it's initialized. Okay? The moment you initialize this class, automatically this gets executed. Okay? So every class should have this init. What is self? It's an instant of this class. In C or C++, this is called as this, quote unquote. Okay? And here it's called self. But you can call whatever you want here. Pythonic convention is that it's called self, but you can have your own keyword. It will automatically understand that the first keyword here is an instant of the class. Then you pass in some parameters of the model. This is typically the parameters of your macro model or parameters of your deep learning model. The example that I have, it's going to be both. And it'll initialize some stuff here. And then you compute some equilibrium. If this is a macro model, then in this part, you would basically compute the capital price, return volatility, so on and so forth. All the modeling part comes here. This is a definition of class. Once you write this, nothing gets executed. This is just definition, right? So the first thing you do is you have a parameter dictionary. Say you have a risk aversion parameter and productivity of the households, so on and so forth. And you instantiate this class here. You pass this params, which is a dictionary of parameters, to this model, to this class model. The moment you write this down, this gets executed. Okay? These parameters that you pass here will get allocated to the instance of this class. And then you can compute equilibrium by calling this instance of the class. That's typically how things are done in object-oriented programming. If you know Python, this should feel natural to you, because how do you compute, how do you define an array? You write np.array, right? This looks similar. When you write np dot something, you're basically calling an instance of NumPy object. You're doing the same thing here, except that since you're an advanced programmer, you've defined your own class. You're not using NumPy, which is developed by Python developers, but you're using something that you have developed yourself. Okay, so how do I update these parameters? Use the syntax, so on and so forth. Then now comparing these two, you can see why this is advantageous. Okay? Now you have model one, which takes in some parameter, and you have another model which takes in different parameter that allows you to compare and plot, so on and so forth. And not only that, you can also save this model as a library. And that's useful for you because maybe it's Friday night and you solve some cool models and you want to call your friend and say, hey, I solved this cool model. But you don't want to send the entire model for your friend to solve it again. What you can do is you can just send the library. And your friend, if he or she is not partying, can open up the library and just inspect it, without running this model. This is important in machine learning because it takes 8 hours, and you don't want your friend to run 8 hours on a Friday night, right? So whenever you solve a machine learning model that takes a lot of time, make sure that you also save it as a library for you to inspect later. Okay? I will show you how it's actually done. And in fact, I'll in the folder, I'll save some instances of the machine learning library for you to upload and inspect. Okay, one last concept before we get into the actual programming, and these are called decorators. This is important because TensorFlow uses a lot of decorators. What is a decorator? It's basically a wrap-up of a function. And it basically takes in a function as an input, it decorates it, and it throws that function. Now, what is a function? A function takes in parameters as input, does some stuff, and throws some variable, right? A decorator is a bit hardcore. It takes a function itself as an input. It decorates the function in the sense that it modifies the function, and it throws function as an output. Okay. And why is this useful? Because in TensorFlow, when you, like I mentioned earlier, I think yesterday, when you allocate A and B and add these two vectors, the computation actually doesn't happen. Okay. What gets done is that memory gets allocated. On the RAM memory, an allocation for vector A is done, and an allocation for vector B is done, and this operation is stored somewhere, but it doesn't get computed. To compute it, yeah. There's something called placeholders in TensorFlow. They are used to basically reserve memory for variables. So when you write tf.placeholder, then all it does is that it just reserves some memory. And this placeholder remembers what kind of operations to do. Yeah, yeah. Any operator, like even if you want to compute functions, it can do. The entire function can be stored in the graph through this operator. And this is important because when you solve partial differential equations, you write loss functions, which can be pretty complicated and nasty, but you don't want to execute them when you write them. So using placeholders is a nice way to allocate memory for the loss. And then how do you execute it? Once everything is done, you pass in random samples of data, and finally you execute it. And for that execution, these decorators are used. So you're building all that graph, and then you send it to a TensorFlow decorator, and that decorator is a hardcore function that takes this graph, sends in the data, computes some stuff, and throws you output. Okay. All right. So this is how a decorator looks like. Now this is your basic function. Okay. You want to compute factorial? Let's forget about what I have here. This is your function. You want to compute a factorial of some number that you pass in. It's going to throw some factorial. That's fine. But you're interested in finding how long it takes. Let's say you have tens of 10 or 20 different functions like this, and for each function you want to understand how long it takes. One way to do this is to write another function called compute time and then pass each of those functions there, but it's too cumbersome. Instead, what you can do is you can write a decorator called calculate time. Okay. This calculate time is defined here. Okay. Here you can see that it takes function as an input. It decorates the function that you send. It computes begin and end time. It prints the total time, and it sends the function as output. Now, for each of the 10 different functions you have, what you can do is just before the function definition, write this line. Then Python automatically knows that this function is getting decorated by this function, and it'll automatically throw you how long it took to run this function. Okay? Why am I showing you this? Because this is how TensorFlow also works. Here, instead of factorial, you will have all the loss functions. But when you write those loss functions, nothing gets computed. But then when you write this decorator called @tf.function, then it gets passed on to this decorator, and it basically executes those functions and returns you input. Okay. I will show you concrete examples later, but this is like the trailer for the tf.function decorator. Okay, any questions? That's right. It's more elegant and it's concise. So all you have to do is just write this one line, right? @calculate time, just before any function that you want to compute running time. Okay, so let's get into TensorFlow now. What is TensorFlow? It's a package that allows you to do nice machine learning computations. TensorFlow is huge. There is reading and pre-processing data packages in TensorFlow. And there is also Keras, which is basically a wrapper for TensorFlow. And there are estimators. You don't need to write your own estimators. You can just call them from TensorFlow library, which is nice. We will mainly focus on this part, but remember TensorFlow is very wide. There is distribution strategy as well. Like I mentioned earlier, if you want to do some parallel computation, you want to have some nice GPU compatible architecture, and that's what TensorFlow provides you, because communicating across different nodes on the GPU is not trivial at all. It can be more time consuming than just communicating with your local machine. So TensorFlow provides you efficient ways of doing parallel computing. I will show you some sneak peek of how parallel computation is done, but we will mainly focus on this. And for solving our macro type of models, this is enough. And we don't need to worry about deployment. That's what software engineers are for. So we are in the business of training the model and solving the model. And so we'll just focus on these. Okay, so how does a TensorFlow look like? Basically, you want to allocate a constant parameter A, and you can just write tf.constant. And it's important to also specify the data type. And if you want to add these two, then you just do this, like tf.add a comma b. But remember, computation doesn't get done. For example, when you print y, you see that it stores this operation add. Okay. but no evaluation has taken place. Okay, this is important for you to know. So we will mostly use float 64 and arrays as well. Yeah, arrays as well. They are kept as arrays. That's correct. Okay, so where were we? Yeah, so how do you execute this then? If everything is just in the memory and you want to see the output, what do? You initiate a session and then you do session.run and you pass y, and this throws you output 3, which has data type tf.float32. Okay, very simple, but it's important for you to know, because when you write a macro model, this is how you write it, and nothing gets executed, and finally you execute the session. And by the way, this is TensorFlow 1. Okay? TensorFlow 2 is better because it works like this, because you're going to use Decorator that I showed you earlier. For example, let's say you have some inner function, and that just basically takes in three inputs x, y, and b, and you do the aggregation here. This is the aggregation part before activation is applied. And you have an outer function, right, that passes in the data y and b to this, as well as x, and computes this aggregation. Okay? The way you do is you just basically pass in the data, and then you send it to this function, which is being decorated, which throws you the output. So I'll post the slides. You can take a look at it later. But what I also want you to do is go to your Google Colab and install TensorFlow. It's just one line, so it doesn't get installed in your local machine. It's just get installed in your Colab, and then I want you to execute these to see how it's actually done. Okay, so it's in the Dropbox folders. You can just import some loggers, and here's where you install TensorFlow. If you can't see on the screen, perhaps you can also take a look at the file TensorFlow. So this just says pip install TensorFlow GPU 2.6.0. You want it to be GPU compatible. Okay, if you do automatically not GPU compatible, and then you want to also want to install Keras. Be specific with the version. If not, then it's going to install some other version, and it's too painful. Okay, when you will see lots of stuff like this. And finally, it will say successfully installed Keras, and somewhere also successfully installed TensorFlow. And then I just want you to play around with the function that I have in the slide, just to see how TensorFlow works. All right, so finally, we will get into the macro model. I was planning to do this on Monday, but let me just show you what we are going to do. Okay? First, I'm going to introduce what kinds of problems that we can solve. Okay? So this is like the general. Now you don't need to understand every slide. I'm just showing you what we will see on Monday. So this is kind of like the general setup that you have. If you've taken Eco 5 to 9, it's going to be very familiar. But if you come from financial engineering or asset pricing, then this is also going to be familiar if you know Merton models. At the end of the day, you're going to have partial differential equations like this, which introduces curves of dimensionality in higher dimensions. And we want to solve these PDEs using deep neural networks. Especially, we want to embed these functions J using deep neural network objects. Okay. I'll show you the overall methodology. This would also be very familiar if you know value function iteration, right? You start from some arbitrary value, you compute policies, you update your value, so on and so forth until convergence. Okay? I'll show you how to embed what we learned in the first two parts